Okay, we'll continue on. On Monday, we did the inverse Cdf method. Okay. And today we'll continue that. So we on Monday we looked at a continuous distribution. We looked at the exponential distribution. And so today we'll take a look at discrete distributions. So inverse Cdf method. This is also known as the inverse transform method. Okay, and here we'll look at the discrete case. All right, so let's say, I don't know, you have a discrete distribution like, I don't know, the binomial, okay? So we'll say binomial, we'll do n equal to 3 and p equal to, I don't know, 0.7, okay? All right, and so so the PMF is defined as what? N choose x, p to the x, 1 minus p to the n minus x, okay? Maybe I'll change this to n is equal to 2 just to make my life easier here, okay? All right, so let's figure out the PMF. We'll have x equal to 0, 1, and 2, okay? And then p of x, as defined by the PMF, we'll have 2 choose 0, 0.7 to the 0 times 0.3 to the 2, okay? And so this becomes 0.09. Then I've got 2 choose 1, 0.7 to the 1, 0.3 to the 1. So that becomes 0.42. And then I have 2 choose 2, 0.7 to the 2, 0.3 to the 0, 0.49. I think I did my math correctly here. Okay? So this is our PMF. And again, the idea behind inverse transform is that we want to be able to generate values from some distribution, even though we can only generate values from the uniform, right? So inverse transform, inverse CDF is, we wish to generate values from this binomial distribution. And effectively, we want to generate zeros with probability 9%, ones with probability 42%, and twos with probability 49%. Okay, well that's simple enough. What we need to do is we need to create our CDF, our cumulative distribution function, okay? And so what do we have? We're going to have our x, and for x less than 0, what is our CDF? Our CDF is going to be 0, right? And then as soon as we hit 0, 0 less than x less than 1, our CDF will be 0.09, okay? And then as soon as we hit 1, until we get to 2, what is my CDF going to be? We're going to add, it's cumulative, so we're going to have 0.51, which is 0.09 plus, oops, 0.42. All All right, and then finally, once we get to 2, what's our CDF? Our CDF is 1, okay, because we'll add in that last 49%. So if I graph this, my CDF looks like this. Let's do that. Okay, so here I'm at 0, and then how do I do this? Okay, and then once I get to 0, I go there, and then at 1, I reach something around here, and then at 2, I'm up there. Okay? So this is what my CDF looks like. All right, so far so good for CDF. I mean, it's just the cumulative sum, right? Okay, what does the inverse CDF look like? Okay, well, we would normally I would take this and I would kind of reflect it around the axis, and so, you know, if I reflect the CDF on the axis y equals x, right, around the line y equals x, what would I get? I would have this business. Something like that. This would be 0, 1, and 2. Okay, except I'm sorry, this is not. I apologize, that's not how it works. Zero, 1. No. Yeah. 0, 1, and 2. So we're good. Okay. And this is 0.09, 0.51, and 1. Okay. Except there's a problem. You can't have a function that looks like this, right? The functions, the rule about the function is that each input on the x-axis gets mapped to one unique value in the y, right? And here we're mapping them to like a vertical segment, which is not possible, okay? So this is not allowed. Each x can map to only one y. Okay, and in fact we have no mappings for anything in between 1 and 1, okay? or between any of the 0.51 and 1 or any other segment. All right, and so this is where the inverse CDF being min of t such that f of t is greater than or equal to u. Okay, so the minimum value of t, this is the case. What that, it basically turns our mapping from 0 to 1 and it maps it as such. So if I've got 0 and 2 and so on, okay, values between 0 and 0.09 will get mapped to 0 because it's the minimum value of t, in this case 0, such that when I plug it into that it will be greater than our u. Okay, so if u is 0.08, okay, 0.08, the smallest value of x that I can use that's going to produce a value that's bigger than 0.08 is going to be 0, right? Because any value between 0 and 1 will produce a CDF value of 0.09. So the smallest value that I can use will still be a value bigger than 0.08 is going to be 0. Okay, and so that's what we have. Okay, and then as soon as I get to if I draw a value that is bigger than 0.09, so if I draw a value like 0.1, okay, well, values between 0 and 1 no longer will produce a value bigger than 0.1. So I have to go up to the next value, and that's going to be 1 will be the smallest value I can use that's going to produce a value of the CDF that's bigger than 0.1. Okay, and that it's going to produce the value 0.51. That's fine. Okay, so everything between bigger than 0.09 and less than 0.51 is going to get mapped to 1, and then lastly, everything bigger than 0.51 and smaller than 1 will get mapped to 2. So here our inverse CDF will produce this. So anything between 0 and 0.09, and then 0.09 less than u less than or equal to 0.51. So we'll get mapped to 0, 1, and 2. Okay, and then so generating random values with this is simple. We're going to generate u from random uniform. Okay, and then you plug in into and then which will equal x, and x will be from, in this case, binomial n equal to 2 and p equal 2.7. Okay, so this is the discrete case. for score method. Is that okay? Have you guys taken a look at the homework yet? Started that? Great. And so in the homework, I have to do a few tests to make sure, or to kind of check if the values you produce from the desired distribution. Okay, and so we have a few tests. A few statistical tests to see if the values we produce, I guess the values in our sample, are from a specified distribution. Okay, and one method is to, for like a continuous distribution, we can use what's called the Kolmogorov-Smirnoff. Okay, so for example, the exponential distribution use the Kolmogorov-Smirnoff test, okay? Also just called the KS test. These are, I think, two Russian mathematicians that kind of came up with this. Okay, it's a non-parametric test to see if our observed data come from some specified distribution, and basically what we do is we compare the empirical CDF with the theoretic CDF. Okay, so maybe I should talk about the empirical CDF. So what the empirical CDF does is it takes your data, let's 100 data points, and it basically says, okay, if you have 100 data points, we can create an empirical CDF by saying each of these data points corresponds to basically the Xth percentile, right? So the largest data point will be at your 100th percentile. Smallest data point will be at your kind of like your 0th percentile, and like the median value in your data set will be the 50th percentile. Okay, and you graph the percentile against the actual value. Okay, so CDF is just graph the actual value of the data point against its kind of percentile value in the data set. Okay, and so you'll get like some kind of like small stair step kind of, if you graph your thing, you're going to get like this little stair step kind of picture here. All right, so this will be like the empirical CDF will be stair step line, okay? And then, we just compare that to kind of like the theoretic CDF, maybe looks like that, okay? And so, this would be an illustration where empirical CDF and our theoretic CDF align quite closely, okay? Okay. Smirnoff test basically kind of measures the distance between the empirical and theoretic CDF and computes out a kind of a test p-value. Okay, and so the KS test, a small p-value. Well, maybe it's helpful to kind of the null hypothesis will be, our data comes from by distribution. Okay, and then the alternative will be our data distribution. Okay, so what would a small p-value indicate? Okay, what do you do when you have a small p-value? Reject the null, right? So then you'd say we would say we have evidence that what? Evidence that our data comes from a different distribution. And on the other hand, a large p-value would then indicate what to us? Not that distribution, but we have no reason to doubt that it comes from that distribution, right? So, the weakness of hypothesis testing is that you can't ever prove the null hypothesis true, but hey, we ran it through the KS test and we don't have any reason to doubt that my randomly generated data is coming from this distribution. So that's what we've got. Okay. So I think I have you guys do that for something. Sorry. On the other hand, for categorical variables, what's a test that we can use to see if our categorical data fit certain probabilities? Is there a test that we can use? Yeah, I heard the chi-squared goodness of fit test, right? Because we want to see how good is the fit between our data and these theoretic probabilities. Okay, so for categories, I mean, there's all sorts of tests you can use, but I think kind of the ones that make sense would be the chi-squared goodness of fit test. All right, and this is a test to see how well our fits specified probabilities.
Okay. Kind of the caveat here is that for goodness of fit test, you want to make sure that the expected count is at least 5. Okay, so for example, okay, so let's just say our theoretic distribution with n equal to 2 and p equal to 0.7, and we said these are the probabilities. All right, 0.09, 0.42, and 0.49. Okay, so if we have 100 samples, okay, then we expect to see what? 9 zeros, 42 ones, and 49 twos. Right? Okay, but on the other hand, if we have only samples, then we expect to see what? Numbers just disappear? What just happened? That's weird. I don't know what happened to these numbers that were in that table there. Okay. But with 20 samples, we have 1.8 zeros, and I don't know, 20 times 4.2 is what? 8.4 ones, and 49 times 2, 9, no, what? 9.8 twos? Okay, thank you. So that's what we, okay, and of course when you actually do your counting, you're only going to get whole numbers. But expected, meaning like if somebody else took 20 and another person took 20 and these things, in the long run, the counts of zeros in each person would be, 1.8. That's what we're expecting. Okay, we would not be able to do the chi-squared goodness of fit test because our expected count is less than 5. And so this will, this kind of violates the large sample condition for the central limit theorem. Because believe it or not, the chi underneath it all relies on the central limit theorem. So anyway, this will break, okay? So anyway, one way around this is you can collapse categories, okay? So work around collapse or combine categories. So instead, let's combine 0 and 1. Okay, and then so we'll say x and the probability of x at 0, 1 will have a combined probability of 0.51, and 2 will have a probability of 0.49, and therefore we expect 10.2 zeros or ones and 9.8 twos. Okay, and then you can do a chi-squared test here. Okay, and And the important thing is, what you have to do is you have to write, chi-squared dot test, and then, this is kind of the vector of observed counts. And then you have to say equal to p, okay? Use the argument p, and this will let you know that the argument p lets R know that you are providing a vector of probabilities, okay? Because test, it can be done for like one group of counts and another group of counts, or you can give it like a two-way table. There's all sorts of things. They're just like variants of the same kind of thing. Specifying p is equal to something where this p is a vector of probabilities that sum to 1. Okay. Then R will know we're doing a goodness of fit test, a test for specified. Okay, if you leave off this p thing, you're going to get some kind of weird error. Okay, and again, if R is going to do some calculations here, and if 8 times your total sample size, if it's going to produce an expected value less than 5, it's going to kick back a warning and say, I don't know if you should do a chi-squared test here, right? Yeah, if you didn't want to do a chi-squared test, you can do like a Fisher's exact test, and that works with permutations and stuff. But I think this is good. Okay. Do we have any questions? Any issues coming up in the homework? Okay. And maybe just why are we bothering with this inverse transform method? Why do we want to be able to generate values from a distribution? Okay, so Carlo methods is that if we want to understand a distribution, like we want to know what's its mean or its variance, or even like what are the most probable values and stuff like that, to understand a distribution, instead of taking the classical mathematical analytic approach of doing integrals and things like that, in Monte Carlo, the Monte Carlo method is to just use randomness to create a large sample drawn from distribution, okay? And that sample will kind of stand in for the population, and you can just take the mean of your sample, and that will be an approximate value for the mean of the distribution. You can take the variance of and that'll be an approximate answer or estimate of of the mean of the distribution, okay? And so R has a bunch of built-in random generating functions, but we want to be able to generate other types of stuff. Okay, so this is not in the homework, but try a practice problem. Like, what if your PDF looks like this? Okay, let's say it goes from 0 to, I don't know, 0.5 to 1. How tall does this thing have to be, right? The total area has to be 1, so it has to have a height of what? Area of a triangle is what? Base divided by 2. Is that right? Okay, so if my base is 1, its height has to be 2. Good, okay. All right, and then so that means what is the function of this line? Is that right? There's two parts to this, right? So x between 0 and 0.5. So our PDF is defined as what? Over here we've got, so 0.5 times x is going to be 2. Or I mean not, if when x is 0.5, the function, all right, it's 4x, right? Okay, so we have 4x over there, and then what is for 0.5 less than x less than 1, what is it going to be? It's going to be negative 4x, but 4, right? Okay, all right, so if this is our PDF, you know, just try this out, right? So, you know, what is this? Okay, and then what's the inverse? And, you know, just all right, this is a good practice problem, you guys. All right, I'm not going to do it here. But, your homework. Maybe I should put it in your homework. But that's good. Okay. All right, we got like 6 minutes left. All right, I'm going to go ahead and just start off this topic, and then we'll continue it on Friday. Okay. Our next topic is going to be rejection sampling, also called accept-reject sampling. Okay, and this is so inverse transform method to figure out the CDF and its inverse. Sometimes that's a hard thing to do. Inverse CDF method requires us to find the CDF, which in some cases doesn't even exist in a closed form, and also to invert it. Okay. This could be hard. So, what rejection sampling does is bother calculating the CDF, okay? Finding the CDF is not required for rejection sampling. So that's an advantage. Okay. So that's, yeah, so this is the pro. It's not even showing up over there. The plus. Okay, but the con is that we throw away some of our values. We reject some of the values. Okay, and you might end up rejecting a lot of values, and so that's, you know, more computational power, right? And the idea is basically this. The big idea, and we'll get into the actual math, is that, you know, here's your PDF. Okay, so this is our PDF, and we want values inside of here. And so we create kind of an envelope. Ideally, this like adjacent to it. And so this is our desired PDF. Okay, and then out here, this is kind of our, I don't know, enclosure. And we throw darts at our enclosure. Okay, we just throw all right, so we'll throw a dart there, and a dart there, a dart there. Kind of over this, we throw darts at the enclosure. And the darts that land inside the PDF, those values are kept. Okay, the corresponding X values are kept. And then the other values are just thrown away. So for the darts that land inside, the PDF region, the corresponding X values are kept as, randomly sampled values. Okay, so maybe between now and Friday, think about, like, it makes sense for producing samples according